Hi all, and welcome to the Year 11 chemistry class. Okay, now I'm sorry I couldn't be with you today, but I'm on excursion. Hopefully this will be just as good, if not better. Okay, now we're going to be starting off with exactly where we left off, and this was talking about the idea that metals are not just one whole large lattice, and that in fact they actually have tiny crystals. Okay, so for example, here we actually have crystals and we've got gaps sort of in between the crystals. Okay, so each of the lattices is described as a single metal crystal. Okay, and the properties of these metals, which we're going to see in a minute, depends on the size of these crystals and also their arrangement. So I'm going to stop us right there, and I'm going to describe it with success passes. Well, not really with success passes, but they are the perfect size to use. So I'm going to describe these as sort of large metal crystals, and I'm going to show you the way they're arranged. Okay, so they might be arranged here like so. There might be a couple of gaps in between. Now, if we just move them over slightly and compare it to smaller metal crystals, such as what I've got here, these sticky tabs. Okay, so we put these all together. They might be arranged, in a similar random orientation. Okay, but something like this. Now, we've got a few of these, and let's compare it to sort of the same, roughly the same size. Okay, so we'll just do a few more to show the effect. Here we go. So we've got two crystals here. We've got two metals here. We've got a metal with large crystals, and then we've got a metal with small crystals. Now, I want us to try and answer this question. So if you can pause the video at this moment and just have a little bit of a discussion about what properties do you think a metal will have with small crystals compared to larger crystals. When I'm talking about what properties they have, I'm talking about things such as which ones will be more brittle. Probably easier if I type it, but anyway, which ones will be more brittle and which ones will be harder or denser. Oops. Yeah, you get the point. So harder, and which ones will be brittle? The small or the large. Okay, so just take a minute. Pause the video. Okay, so I hope you had a good discussion about it. Let's have a look at these again. Hopefully you said something along the lines of, if I just grab a piece of paper, hopefully you said something along the lines of smaller crystals versus larger. So smaller crystals should be more brittle. That means break into pieces easier, and larger crystals should be more malleable. Now we compare their hardness. Small crystals should be harder or denser, and larger crystals should be sort of less hard, less dense. Now, if we look at why this is the case, okay, we look at our crystals. We have the smaller ones. We said that smaller was more brittle. Now, we look at where the crystal is likely to break, and really it's these points of weakness here. Okay? Here, here, and here, here. So the gaps in the crystal, points of weakness, where the metal can break. Those with the smaller crystals have simply more points of weakness. So you can see here 1, 2, 3, 4, 5, 6 compared to only 1 point of weakness in the same size. So more chances where we can break it. Whereas the larger ones have less points of weakness. So we'll write that under smaller. Why are they more brittle? More gaps. And larger, more valuable, less gaps. So less likely to break. Then we look at why small crystals are denser. And hopefully you were thinking something like, because they're small, you can fit more crystals in a small amount of space. Or in other words, the gaps are smaller. Even though we have more gaps, they are smaller. And we've got this crystal with a larger gap. It's got less gaps, but it's larger, meaning it's less dense. So smaller is smaller gaps, and this is larger gaps, so less dense. Okay, let's compare that to our results of the quenching and annealing and tempering prac that we did with the needles. Okay, now when we're talking about those different techniques, we'll go back to this slide that actually said what the techniques were. Okay, so something like annealing, you know, the metal is heated. When it's heated, the metal starts to melt, the cations start to pull apart. Okay, and then when it's allowed to cool slowly, our results should be that this was the most malleable. Okay, and you should go back to crystal size. What I want you to try and do is describe what you saw here. So the results we should have gotten is that annealings were more malleable, quenching was more brittle, and tempering was sort of in between. What I want you to do is pause the video and discuss why annealing is more malleable, why quenching is more brittle, and why tempering would be in between. Press play when you're ready to hear the answer. Okay, so hopefully you said something like this. When they're being annealed, the metal melts, but because we're allowing it to cool slowly, it has time for the crystals, for the metal cations to bond together and form a regular crystal structure. So when it's melted or close to it, the cations pull apart. So if we allow it to cool slowly, they have a longer time to come together. Whereas with quenching, they're pulled apart, but because we cool it so quickly, they have less time to come together, resulting in smaller crystals. So, hopefully we got these results. Annealing, the metal is softer or more malleable with improved ductility. Larger crystals. Quenching, harder and brittle, smaller crystals. Tempering, metal is harder but less brittle. So it's something in between, crystals of an intermediate size. And we'll show you this through these pictures. So when you anneal, you heat the metal, the cations pull apart, but because you allow it to cool over such a long time, they have the chance to bond together into larger crystals. Now, if they're bonding in larger crystals, remember the gaps are larger, making it less dense, but there are also less gaps all up, making it less brittle. When it's being quenched, the cations pull apart, but we freeze it straight away, not allowing the cations to come back together quickly, meaning that we have smaller crystals with much more gaps, okay, but the gaps are smaller, meaning that the metal is harder, more brittle because it's got more interfaces between the metals, it's got more points of weakness. Okay? Now, if we have a look at tempering, it's simply an intermediate because what you do is you quench it and then you anneal it, giving crystals of an intermediate size, meaning that the metal is harder because it's got small crystals and it's more dense, but it's less brittle than quenching by itself because it has less gaps because they're slightly larger crystals. Okay, so we already answered that one. One thing I did want to do before we move on is have a look at another way we can modify metals, and that is through work hardening. Now, I would have loved to get you guys to do this, take your anger out on a safety pin, a paper clip, but I'm sure you'll be able to do this at home once you get a paper clip. Okay, so if I open up this paper clip, you'll notice, it's quite malleable. Okay, I can bend it. But as I start to bend it back and forward, it actually gets a little bit harder to bend. Okay, this is called work hardening, making it harder to bend by working it. And then eventually the paper clip breaks. I've actually made the metal harder, but I've also made it more susceptible to breaking. So I've made it more brittle. Now, we've got to explain that with crystal size. Okay, you can pause the video at any time and have a discussion if you like. But what happens is the metal is malleable at first. The crystals are, large. They haven't been tampered with. But then when I bend it, I actually break the crystals up into smaller pieces. If I break the crystals up into smaller pieces, they fit together closer, less gaps, making the metal harder. But if I break it into smaller pieces, eventually the metal will have so many gaps, the crystals will have so many gaps that it becomes very brittle and very susceptible to breaking. So if we'd like to write a couple of board notes on that. So hammering, bending, or otherwise working the metal, it disrupts the lattices. It makes more crystals of a smaller size because you're actually breaking up larger crystals. It makes the metal harder because there are smaller gaps, so the metal's more dense, but it also makes it more brittle. Okay? Okay, so we're actually going to work on the next PowerPoint now, and that is ionic bonding. Okay. Whoopsies. Whoops. Sorry about that. Okay. The first thing I want us to do is discuss this topic. Now, just bear with me for one moment. I need to collect my resources for this lesson. Okay, so finally, chapter 6, ionic bonding. Okay, so if we'd like to just open up our books to a new page and just write down the heading. Oops, write down the heading. Chapter 6, ionic bonding. Okay, now the way we're going to start this is by drawing on your prior knowledge. We learnt about metallic bonding already. We know that metallic bonding occurs in metals. My question is, what does ionic bonding occur between? Really, we only have two options, because metallic bonding is between a metal. So really we can only go, is ionic bonding between a metal and a non-metal? Or is it between non-metals? There are only options. Hopefully we're thinking this option, a metal and a non-metal. Okay, now let's have a look a little bit about ionic bonding. Now, I want us to start this lesson by actually doing a mix and match of a table. So if someone can please grab out this envelope from the CRT package that I left and open it up, there'll actually be some, jigsaws that people can put together in groups of, I'd say, 3 at their tables. Okay, now what I want you to do once you open up the package is find the heading structural information and property. Basically, I want you to put this table together, okay? Basically, the way we started talking about metals is talking about their properties, okay? And then we spoke a little bit about what does their structure show about their properties. So what I want us to do is match things together, okay, in terms of property and what information that tells us about their structure. Okay, so give the class about 5-10 minutes to do this, discuss it, and then come back to the PowerPoint, to the video. Okay, so hopefully you've had enough time to put it together, and we'll go through the answers. So we've got property here and structural information here. Let's have a look at the first property. Sodium chloride, an example of an ionic compound, which we've been looking at in all of these cases. It's hard, okay, but it's brittle, meaning it smashes into lots of pieces. What does that indicate about the structure? It must indicate that it's not like a metal in the way that the electrons can follow the cations. It must be that the bonds are specific and they don't allow readjustment. Okay, so we should have had something like this. Because they're hard, the forces between them are strong. Yeah, that explains them being hard. But they cannot adjust themselves when the particles are moved. So they're not like metals in that case, in that when the cations move, the electrons follow. These ones, they must all be stuck into a particular arrangement. If we have a look at another one, sodium chloride does not conduct electricity in the solid state. Okay, Now, why do metals allow sodium chloride to conduct electricity? And the reason being because they've got the delocalized electrons. So to conduct electricity, you need charged particles. Okay, so basically it means that there's no charged particles, no free moving charged particles are present. Okay, if we look at another one, sodium chloride does conduct electricity in the molten state, so when it's a liquid. This indicates that free moving charged particles are present. Okay, and how about sodium chloride has a high melting temperature? Well, if it has a high melting temperature, it must mean that forces between the particles are strong. Sodium chloride is not lustrous. Remember, in metals, the reason why metals are lustrous is because their delocalized electrons reflect light. So in this case, there must be no delocalized electrons. And then finally, sodium chloride forms cubic crystals. It has a crystalline structure, meaning that there must be some sort of ordered crystallized lattice. So hopefully you got those ones. And yeah, be proud of yourself if you did. Okay. So we're going to use the ionic bonding model that we develop to explain these properties. Okay. To explain these properties. Now, we're just going to write down a few of the properties to summarize. So properties of ionic compounds. So number one needs to be something like brittle. Another one should be that ionic compounds are not lustrous. In other words, they're dull. Conduct in liquid state. Don't conduct in solid state. Okay, and form crystals and high melting point. We need to be able to explain all of these properties using our idea of the ionic bonding model. Now, we're going to start off here. Okay, oops, let's get through all of these. We just went through those. What I want us to do is go back to the start, and I want us to draw out sodium. Okay, give yourselves a few minutes to do that. I want you to draw all of the protons and all of the electrons and all of the neutrons. And now, if you don't know what isotope of sodium I'm talking about, that's a very good question to ask. I want you to do sodium 23 and 11 as sodium's atomic number. Okay. So hopefully we've got something like this, where we've actually got, where we've actually got 2 electrons in the first shell, 8 in the second shell, and then 1 in the third shell. Sodium is in period 3. It's got 3 shells, and it's in group 1. It's got 1 valence electron. Okay, now if we have a look at this, we may ask the question, why does sodium actually want to form bonds? Why is it so reactive? And this should be the reason. It's got one electron in its outer shell. It is not stable like that. Okay. Now, this is the way we're going to do it. Oops. Sodium. We're going to actually write it out like this for all of them. So I just want you to write examples of forming ions. Okay, so examples of forming ions. Number 1 is sodium. We're going to actually do element here. We're going to find out number of electrons in outer shell. And then we're going to write down choices and then ion. Okay, so this is the element. Number of electrons in its outer shell. So it's got 2 choices each time. It's got 1 electron in its outer shell. Okay, let's look at sodium again. 1 electron in its outer shell. Its choices are 2 things to gain a full outer shell. The choices are lose that 1 electron or gain 7 electrons. Okay, so let's write that out. Lose 1, gain 7. Now I hope you are all thinking lose 1. Okay, atoms are lazy, they do the easiest route. Now that's not actually the reason why. The reason why you should all be thinking of is because sodium has a low core charge, okay, meaning that it would rather lose the electron than gain it. It doesn't have such a strong pull on electrons. Anyway, if it loses electrons, so if you lose electrons, you will be positive, more positive. If you gain electrons, you are more negative. So here the ion should be Na+. Okay, let's have a look. Sodium loses the electron. Oops, now it only has 2 shells. Okay, why do atoms want a full outer shell? We've spoken about this before. So they are stable. Okay, it's the lowest energy state. It's the noble gas configuration. I'm full and I'm stable. I always tell my year 10s, it's like a spider. Imagine if a spider had 7 legs. It'd be falling all over the place. It needs those 8 legs to be stable. Alright, now if we have a look at this one, I want to ask the question what atom this is. Now you can tell simply by counting the electrons. 2, 10, 15. So which one has an atomic number of 15? And of course that is phosphorus. Okay, phosphorus has 5 electrons in its outer shell. It can either lose all 5 or it can gain 3. Now we know phosphorus has a core charge of 5 as well, so it's much more likely to gain 3. And if it gains 3, it becomes P3-. Okay, over here, yep, and here come the electrons out of thin air. Where are they coming from? We'll find out in a minute. Okay, now let's do another one. Which element is this one? 1, 2, 3, 4, 5. Okay, so we have boron. Boron is B. It has 3 electrons in its outer shell. It can either lose 3 or gain 5. It has a low core charge, so it's likely to lose the 3, becoming B3 plus. Let's look at it happen. Boron, yep, bang, 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 1 shell less, and B3 plus. And now it's an ion. Now we have to talk about what the ions are. We did this in Head Start, but if you've forgotten, cations are the positive ions. Think of the T as a plus, or people like cats. Some people think about it like that. And anions are the negative ions. A negative ion, anion. Or some people think onions, like onions, make you cry. Okay, what I want you to do is give the students roughly 15 minutes to try and work out the charges on each of these elements when they become ions. Okay, just like we did before, try to work that out. Okay, press the pause on the video now. Okay. Okay, let's actually write this out. Aluminium, 3 electrons in its outer shell. It will lose the electrons and become Al3 plus. I'm actually not going to write in that color because it's not coming out well. Maybe a blue. Sodium has 1 electron in its outer shell. It will lose that 1 electron and become sodium plus. Bromine has, let's just try and go black. Bromine has 7 electrons in its outer shell. It will gain 1 electron and become Br minus. Sulfur has 6 electrons in its outer shell. It will gain 2 electrons to make 8 and become 6,2 negative. Carbon, 4 electrons in its outer shell. Quite strange. Because it's got 4 electrons, it can actually go either way. It can gain 4, so becoming 4 minus, or it can lose 4 and become 4 plus. Okay, so that's just something to be aware of when you're looking at carbon. And it actually does go either way, which is interesting. Alright, now if we look at silicon, silicon's very similar to carbon in the way that it actually has 4 electrons in its outer shell. So it actually does the same thing as carbon, surprise, surprise, being 4 minus or 4 plus. Now if we move to helium, helium we notice is in group 8. It has a full outer shell. It will not form an ion. So I guess that's a trick question. Iodine, I minus, and then oxygen, 6 electrons, so it gains 2 to become 2 minus. Nitrogen has 5 electrons, so it will gain 3 electrons to make it 3 minus. Phosphorus has 5 electrons again, so it'll do the same as nitrogen. It's in the same group. Neon, no ion because it is a transition. It's a noble gas. Then we've got lithium. Lithium will form a positive ion. Chloride is negative. Calcium is 2 plus. And fluoride has 7 electrons. Fluorine has 7 electrons in its outer shell, so it'll gain 1 to get that full outer shell. as a minus. Okay, so I hope you got those ones right. Now we might be asking this question. What patterns do we see? Okay, which elements actually in the periodic table would make cations and which ones would make anions? Okay, actually even try and just say which groups. So, because groups 1 to 3, low core charge, more likely to lose electrons, they will actually form the cations. Groups 5 to 7, the anions. Group 4, either way. Group 8, nothing. Okay, how about groups 4 and 8? We just said that. This is showing you the Hindenburg disaster. Okay. Spoke about this just ever so slightly. Basically, they filled up a blimp with hydrogen. You know how reactive hydrogen is. It has that one electron in its outer shell. If you filled it up with helium, as they do often now, you wouldn't have had that problem. So, groups 4 can go either way. Group 8 is already stable. Okay. Now, the question we really need to ask ourselves is, where do these electrons come from or go to? You can't just get rid of these electrons in thin air, and you can't just pull them out of nowhere. And the answer is the atoms actually interact. So this is a little funny joke. It actually says, that guy's saying, perhaps one of you gentlemen might tell me just what is outside the window that you find so attractive. And it's actually positive ions inside attracted to the negative out via a beautiful electrostatic attraction. Okay, we spoke about metallic bonding, and we said that basically they don't want their valence electron, so you can try and think of it like they're playing ball with each other. Get rid of this electron, get rid of it. Ionic bonding is different. It's much more romantic. It's actually one guy giving electrons to another guy. Okay? So what happens when they react? We're going to look at an example of sodium reacting with chlorine to produce salt. Show you this reaction in real time. Very violent reaction, and you can see the layers of salt at the bottom of it. So let's have a look at what happens. What I want you to do is write down the heading. Oops, my pen's becoming. I want you to write down the heading electron transfer diagrams. It really helps us to understand ionic bonding in this way. Now, just one moment. Okay. Now, we'll do the sodium and the chloride for one example, and I'll show you how to write out an electron transfer diagram. Okay, so let's say we've got sodium here. Sodium has one electron in its outer shell, whereas chlorine, chlorine has 1, 2, 3, 4, 5, 6, 7. Okay, just imagine it like a marriage made in heaven. We've got sodium, which has one electron in its outer shell. Now, these are often called dots and cross diagrams because to determine where the electrons came from, you actually use crosses on one and dots on the other. Okay, it's always one type of metal bonding with one type of non-metal. Anyway, we've got sodium here. It wants to lose that electron, chlorine wants to gain that electron, marriage made in heaven. We put the arrow over here. So this is how we do an electron transfer diagram. We then do an arrow and we show what the products are, which are sodium, which is now positive because it's lost an electron, and chlorine, which is now negative because it's gained sodium's electron. But we actually have to draw out chlorine's outer shell. With sodium, because it's lost its outer shell, we just draw its empty one. Okay, and we show that the electron's gone there. Okay, now if you want to have steps in writing out these flow diagrams, these dots and cross diagrams, you can. Okay, so give students a bit of time to write this out. Show only the outer shell electrons using a different symbol for the electrons of each atom. We then do an arrow showing the electrons moving. We then keep the original electron symbols to show where they came from. And then we add charges. Okay. Now we'll do another one. We'll do magnesium and oxygen. Here you can see magnesium has 2 electrons in its outer shell. Oxygen has 6. You guys can pause the video at this stage to draw out the electron diagram. Okay, now that we've come back, we'll do it ourselves. So the electrons go both towards the oxygen, and the products are Mg2 plus and O2 minus. So hopefully you had that. We'll do another example. Okay, so example 3. Oops. I want us to do magnesium with 2 electrons in its outer shell. And I want us to do chlorine with 7. I want you to try and pause the video and complete this electron dot diagram. Okay, so hopefully some of you figured it out and realized that magnesium has 2 to give, but chlorine only has 1 to take. So we actually need 2 chlorines to overcome this. So what we do is we draw in another chlorine. We put one magnesium's electron there, and we put the other one there. So our products will still be Mg2 plus, but they'll actually be 2 of the Cl minuses. Oops. Okay. So, just show that here. Yeah, so you need 2 of them, and there you go. Okay, so my question is then, why do they stick together? Why does the sodium and chloride stick together? Why doesn't the sodium, once it's happy with its 1 electron, gone, just leave? Now the answer is opposites attract. Okay, we've heard about it time and time again. But no, in all seriousness, we know that positive is attracted to negative. We know that from when we did metallic bonding. So we call this the ionic bond. And it's where it refers to the electrostatic attraction between positive cation and negative anion. Okay? So that is the actual ionic bond. Now, we can just look at this, just to further reinforce it. Oops. For example, here, potassium and fluorine. Potassium has 1 electron in its outer shell. Fluorine has 7. Marriage made in heaven. And potassium's electron moves to fluorine, making fluoride and potassium positive. Then they will stick together. So this point down here is a word we have to use. Another word for the charge is valency. You'll see it pop up. So for example, Mg2 plus has a valency of +2. It's the same as saying it has a charge of +2. Okay, so that's just a bit of terminology. Okay, now what we are going to do, I think, is a little bit of work from our textbook. Okay, so if I get the sufficient questions. What I want you to try and do is chapter 6. I hope I can just bring it up. Chapter 6, we should have it here. Oops, not year 12. Where is it? Year 11 textbook. So it's in part 1. No, it's not. It's in part 2. I lie. I want you to actually try these questions. Question 6. Question 6. 7 and 8. So 6, 7 and 8. Okay, 8's a bit of an extension of the knowledge, but try those out and then come back to the front. Okay, now one more thing we have to get through in ionic compounds is actually writing out the formula for them. Okay, so not just the electron transfer diagrams, it's the actual formula. Now, we have these rules. Okay, we're going to follow these rules. First of all, I actually want you to write them out. You're going to retain it for longer if you write it out. Okay, so the first rule, cation always goes first. Blah, blah, blah. So actually just write these out. So pause the video, write these out, and then press play. Okay, so as we're going through these rules, we're going to answer an example. So I hope you've got your formula rules there with the heading formula rules. And now I want you to put examples. So I want you to actually have, oops, find a new page. I want you to have examples. So formula examples. Okay, so First example, we're going to do sodium oxide. Okay, now the rules are, let's follow the rules so we know what we're talking about. First rule, cation always goes first. Identify your cation and anion and their charges. Their charges are in superscript, up the top, super at the top. So, sodium oxide. Our cation is Na plus and our anion is O2 minus. Okay, now our charges are +1 and -2. Okay, so we've done step 1. Step 2. Positive and negative ions are combined so that the number of positive charges equals the number of negative charges. Okay, so here you can see that we've got a -2, but we've got a +1 here. So we actually need to insert another sodium so that we have +2 and -2. So those equal 0. We then need to write the number of each ion to achieve neutral in superscript after the ion. In subscript, sorry. So, to tell people we have 2 sodiums, we write Na2O. Let's just focus this. No? Okay. Na2O. Alright. Let's do the next one. Let's do magnesium phosphide. Mg2 plus and P3 minus. So the charges are +2 and -3. This definitely does not equal 0. If we have a look at it, we have more negatives than positives, so we actually need to add another positive. Now we have +4 and -3. Still doesn't equal 0. Now we have more positives, so we should probably add another negative. Now we have -6 and +4. So we now have more negatives. Let's add another positive. Now we have +6 and -6, which does equal 0. Good for us. So let's tell people what the formula is in subscript. Mg3 P2. Great. Now, we've got to talk about something such as polyatomic ions. In year 11 and a lot of year 12, you don't need to memorize the formulas. Polyatomic just means that the ion is made up of more than one atom. So let's write that out. Polyatomic ion made up of more than one type of atom. Whereas we've got monoatomic ion, where the ion is made up of one type of atom. An example of polyatomic would be SO4 2- sulfate. An example of monoatomic is chloride. Some other examples of polyatomic are like so. They need to just be treated like a whole ion, okay, by themselves. Now, we'll do an example with a polyatomic ion. Let's do ammonium phosphate. Now, if we find our cation, ammonium, you don't have to know off by heart, you'll get this table. It's NH4+. So, NH4+. Phosphate is PO4 3-. So, we follow the same steps. Find your cation and its charge. Now, this 4 is not part of its charge because it's subscript. So it's talking about how many hydrogens are there. So its charge is actually +1. This phosphate, the 4, talks again about how many oxygens are there. So its charge is -3. Now, because we have a +1 and a -3, we don't have 0. We need to actually make sure we have 3 of the ammoniums. So, how do we tell people that we have 3 ammoniums? Is it like this? And the answer is no. For polyatomic ions, you need to put the ion in brackets and then put the subscript after the brackets. Okay? So, we'll show an example here. Instead of saying we have 43 H's, by putting a bracket there just before the 3, we actually have 3 ammoniums and 1 phosphate. Okay, now this final hint, they swap superscript numbers. I'll show you what that means. Let's say we're talking about potassium, let's go potassium oxide. Okay, we have K+ and O2-. Now, they swap superscript numbers, so it's K2O. But let's see if that works out. K plus O2-. This is +1, this is -2. We need to make sure we have 2 of the K pluses. Oops. So +2 -2, meaning it's K2O. So it does work out like that. I guess the only problem you'll get is if you do, let's go magnesium carbide. Now, if they swap numbers, it's Mg4C2. But if we do it the original way, this is +2, this is -4. We need to have 2 Mgs. It's Mg2C. That's the correct way. But you could just do it like this and then simplify, because you divide by 2 on both sides. Okay, now let's have a look at some other examples. Yeah, we've got some just funny jigsaws, putting them together, yep, making sure the charge is balanced. Basically, if you get those, they're fine. I would pause the video at this stage and just write out the ionic formula of these. So press pause. Okay. Another case is transition metals. We said that transition metals can have multiple types of valencies. they will tell you the valency in brackets. So for example, copper 3 means it has 3 electrons in its outer shell, loses 3 and becomes copper 3 plus. So for example, let's just say we're talking about iron 2 oxide, and then we're talking about iron 3 oxide. In this one, it's Fe2 plus, O2 minus, so it's just FeO, and in the bottom one, it's Fe3 plus and O2 minus, so it's Fe2O3. So it'll give a different formula because they have a different charge. And then just finally, once we're up to that, I want us to try and do the rest of chapter 6 if possible. If you run into questions on its structure, just skip those for now because we're going to do those at a later date. Okay, but practice as much as you can. So let's have just a quick look at it. So all of these questions you should be able to do, including, so not up to uses, so all of those, these, and yeah, these as well. So don't go to the ionic bonding model. Just go to ion formation and formulas. So do these ones, whatever it says on your questions to do each week. And yeah, just give students a bit of time to work through those textbook questions. Okay, well, I hope you enjoyed it, and I will see you guys soon.